So I won't introduce myself. I think you've heard me talk enough, and if you have more questions, look me up online. I want to talk about cross-platform development. And I think the first question that comes to mind is, what exactly does true cross-platform mean? Because each one of us sometimes gets to work on some subset of what could generally be called cross-platform. But I wanted to enumerate maybe just a little bit more of what some people expect, but this is also still a subset of what you might, basically anything that any silicon or any compute device that you can run software on. So if we go to the lowest level, you're talking about ASIC, really custom designed chips. We have embedded systems, which are, again, very small chips running in our, all the way from our washing machines to routers. Of course, mobile devices are probably the most popular embedded devices in consumer markets. And we're also starting to talk about operating systems, because not, even though the chips might be the same, you have a different environment where your software is running. And popular OSs might be iOS or Android. On desktops, of course, we have Windows, Linux, OS X. But there are many other different types of things that you might have not come across that are still platforms that I've personally had to write software to run on. And that might be something like browsers, which are becoming a de facto platform today. I had the dubious pleasure of writing browser plugins. That's not really a thing anymore. Google tried Knuckle a while ago. Of course, JavaScript is, I guess, sort of the de facto scripting language of the web, although WASM, that's a WebAssembly, that's pretty much the JavaScript killer for anything that's not front-end UI. That might be a bit controversial, but talk to me in 5 years and we'll see where we're at. And of course, going to the cloud, total backend, we have servers, we have Docker images, we have Node.js services, which are like DLLs running somewhere. Of course, serverless APIs. All of these things are compute interfaces and compute devices that we might need to target our platform, our software to. And beyond those, you can think about vehicles. There's some of these things, vehicles, Internet of Things, robots, and of course targeting things like CPUs, GPUs, all kind of different hardware configurations, heterogeneous computing. These are all things that we come across when we're working with software, and especially when you're doing C++. I think people mentioned here that probably the most important reason for using C++, and I think it's more of an if and only if type of statement, is for performance. And I would add that C and C++ are probably the only viable languages for true cross-platform development. I hope I'm going to convince a little bit about this in this talk, because anything that has silicon can run C code. So and if we think of C as more or less a subset of C++, then the rest of the things that you might see always boil down to that. And I'm going to talk about how we design software to run on lots of different platforms. I've had the opportunity to target most of or many of these items, not all in the same project, but I did write software that runs on Windows, Linux, OS, inside the browser, on mobile phones and on servers. The same exact piece of C++ code running in all these devices, just everything is built separately. And that's not such a big deal. The big deal is how you actually manage this type of software system, how you build your project, how you architect your system, because there's a lot of challenges doing such a thing. Now, when we go to various websites where we read about platform APIs, if you go on code projects, a lot of you probably are familiar with it, or MSDN, go to the Qt examples, of course on the mobile device, iOS, Android, and even if someone is familiar with the ROS, something I've been playing around lately, there's a huge mix of concerns when you look at these examples, because these examples are often designed to teach you some API, to teach you some functionality, but they don't take into consideration what real code in a real product or real project needs to look like when you're actually maintaining this project with multiple people, multiple versions and releases. And the result of this code is something that's extremely difficult to refactor because it mixes so many different aspects of the software. It's a maintenance nightmare. It's almost never truly portable. I think some of you mentioned it earlier in one of the talks. Extremely difficult to test this code. And of course, bug prone because there's many different things and different people are familiar with other things. And one of the other things that has not always come to mind is that we're mixing of skills. So a person who is an expert in doing Windows MFC UI programming isn't really the right person to manage some of the code that does business logic. So, and a lot of these things mix data structures with algorithms with particular APIs. And to make things even more complicated, when you go into module boundaries, that is DLLs and shared libraries, you have problems related to error handling and things like exceptions and a lot of potential undefined behavior, friction boundaries. Now, I'm going to present something I call the Salami Method, and like I say here, it's born of frustration, blood, sweat, and tears. So this is something that an architecture that I developed working on multiple projects over several years, where I sort of managed to abstract some of the concerns related to architecting such multi-platform or cross-platform system. And I'll show you that it makes it easier to build these systems, to test them, to debug them, manage and maintain them, and really be able to focus on your effort in such a way that keeps you sane. Or at least you spit the blood only once, and then you know it's going to hurt just once. So this is really the gist of this talk. So if I had to print just one slide and put it on my cubicle wall, this is the slide to do it. You can. I personally had the chance to actually use it as a reference in my work. The reason I call this Salami Method is because we're going to show these separate, very, very thin layers of concerns, layers of abstraction, each one built on top of the other. And I'm going to talk about different aspects of each one of these layers during this talk. So at the bottom, we're going to see the cross-platform code and the way we test this code. And then we're going to rise up within these layers and see what each one of them means, why we use it, and what its role is. Now, this is kind of an abstracted view. Most systems don't actually need to implement all of these layers as separate layers in your code. It's very common that you would merge some of these layers because it's more natural, and especially when you're not really targeting 200 different platforms. Nevertheless, it is important to keep in mind that all of these concerns don't go away. So if you are making thicker slices, you still must be aware and keep in mind that they never went away. So all of these concerns, if you remember the OSI 7 layers of the networking OSI, this is kind of similar in the same way that it abstracts different aspects. And even if you don't implement them in your code, it doesn't mean that they don't exist there as abstraction. So the reason we want to do this slicing, and I think this is sort of the end of my introduction, is, of course, the dry principle. Don't repeat yourself. I don't know how many of you have had this, tell me, raise your hand if you've seen this before. I've worked on several projects where there was one thing doing the iOS version and another thing doing the Android version, and they were basically implementing exactly the same app from scratch and competing to fix the same bugs or different bugs and trying to fix inconsistencies between the two apps and chasing each other in releases. So that's a violation of the dry principle. We want to keep as much of the common code common. And again, this brings us back to C++, because if you want to write iOS and Android, C++ and C is basically the only option you have. as I said before, single responsibility and testability, that means transparency. It means that when we separate our code, when we split it up into separate thin slices, then it's always clear where the problem comes from and how you fix it, because it doesn't have a lot of different unrelated aspects mixed in the same layer. As I said, consistency, we want the business logic isolated and shared. So isolated in the sense that it doesn't get combined with aspects related to platform, APIs, and hardware, and shared in the sense that it's the same code can run on the iOS app, on the mobile, on the cloud, and on the server. Once we do this abstraction, it's so much easier to develop to new platforms. So say we're working on a photo editing app, and suddenly somebody decides that we're going to target Microsoft Surface devices, then maybe all we need to do is just fix the native UI, but the rest of the logic remains exactly the same. Developer skills I've mentioned before, give different people different parts of the project where they're good at, and you're really leveraging the assets of the company. If you're giving someone who is a UI specialist to do algorithms, you're really not using your assets, and it also affects, of course, developer happiness in whatever they're doing. So this is also part of a byproduct of the system. And of course, refactoring. When everything is modular, it's much easier to refactor. Right. So at the heart of our system is our cross-platform C++ core. This is the reason that we're developing this system. This is maybe our IP, the apple of our eye. This is what we have the patents written for, and what we want to share amongst all of our target platforms. Now, at this level, this is where we apply our design for patterns, the beautiful idioms, all the clever code, all the intelligent algorithms. We structure everything based on the architecture of the internals. And we live in this beautiful, colorful world of portable C++ code. I'm saying portable because we might be able to build it on multiple platforms as separate static libraries. Doesn't necessarily mean it can interact with the outside world, but it's possible to do it on most platforms. Yeah, the question?
Yeah, when you say this is the beautiful items, but supposing one platform has one compiler, the other platform has another compiler, which is obviously the case, and they're not exactly compatible. This compiler doesn't implement that feature that you want to use here, and the other one doesn't. So what happens is it usually this degrades to the lowest common denominator, and you start writing C+ here.
Okay, I can accept that remark. In this sense, I said we're living in a beautiful world, so let's assume all the compilers are compatible.
Standard C++.
That's actually
standard? What is that?
No,
11, 14.
Yeah, no, but I think that's what you're mentioning. It is a problem, but it doesn't go away if you do it the spaghetti way. Right?
No,
so it's kind of orthogonal to what I'm talking about. But you are right. You do need to hope that you can target your portable code to the platforms you are targeting. But these days, most platforms actually support LLVM and Clang. You have a lot of different targets, so that actually makes. I think we are improving. I'll say it this way. Okay? But you're right. And of course, in this case, I hope everybody here is writing tests, lots of tests, and this is the place where you do unit testing.
So in general, again, you're saying that you're developing a common infrastructure that you want to build on each and every platform independent, and then you're building your business logic in one way, and that's what you gain? That's the main idea?
More or less, yes. Assuming we have some, basically any software system that has some kind of logic that you want to move to different platforms. It could be image processing, it could be an accounting system, it could be a trading system or banking system. Assuming the logic is, we're with C++ discussion here, so, and because C++ is very often the only thing you can actually use. So that's actually one exception to the rule. Sometimes that's the only option you have, so it's not totally only performance.
Yeah, but C++ is not a language anymore. C++ is a platform. You have C++98, you have C, which some platforms have only C. You have C++ 98, C++ 103, and then you have all the new goodies, which you always want to use, but not every platform chases those goodies. So if you want to write some,
but you have to live with the system that you have. But you live with the systems that you have, and this is kind of orthogonal.
It's kind of true, but what happens is that within this code you start writing if-defs. If you are on that platform, then this is how you write the that's what look at the boost code, which should run on everything, right?
No, but this is another design issue. But
yes,
I think abstract it away. You have to. I want to create an array somehow, and then on one platform you have STD array, and one platform you have the array you say.
So you end up writing your own stuff. You want to write STD array. You want to write it beautiful, not your array. You want to write STD
Yeah, but again, I think this is kind of orthogonal to what I'm talking about, because it would happen regardless of what your code looks like. So if you're already in a position where your product is multiple platforms, you have to make sure that you can actually deliver that, right? And I'm trying to show you, assuming you can do it, maybe a better way to do it, or one good way to do it. Now, let's move on to here we see the same diagram again. We're going to be rising up in our levels. So the second layer is what I call, it's the cross-platform public C++ interface. And this is a bit of a subtle kind of layer, because this is the C++ API, and here I think the word API is more important than SDK. This is where the distinction happens, because here we're thinking about the design principles that focus on the consumers. So whoever is going to be using our library, our static library from some kind of app, from some kind of service, for example, how are they going to use my core C++ code? And that's why I call it the public C++, because here I can actually hide a lot of my implementation. I can, even if we know the platform, we can deliver binaries, we can use pinpool idioms, we can use modules. This is classic case where you would actually stick modules. We haven't had a talk about modules yet, but hopefully we will soon. You can hide proprietary code, dependencies. I've had customers who didn't want boost file system in the API, or boost shared pointers. They wanted boost STD shared pointers, or file paths, or different kind of thing. This is the place to do it. And the nice thing is that it completely separates it from the public, the C++ API that you wrote in your own internal system. So it gives you another layer that can abstract it for your customers. And the things that you're considering here are completely different. Things like initialization and shutdown. How do you allocate resources? How do you deallocate them? Of course, these all mean different things, but think about DLLs that need to allocate some memory or some resource within the DLL memory space. So all of these things are things that you don't generally think about when you're doing like your own library. You don't necessarily think about them, or if you do think about them, you don't think about them in this context. Of course, lifetime management, sessions, configurations, how do you serialize or deserialize, how do you initialize from some file system, all of these things are things that become extremely apparent at this layer. The type of testing that you do here is obviously not the functional testing that we did at the lower layer. Here we can do mocking, and we can do some unit testing on the API itself to make sure that it actually does what we expect it to do.
What did the first one do? Sorry, I missed the difference between the first layer and
the first layer is the algorithm. It's the IP. It's the business logic. Okay. And here we're really wrapping the business logic in a way that we can sell it to the customers, to the consumers. I will say again, very often, and even if we have time, I'll show you an example at the end. This layer doesn't always appear as a separate layer in your code. It really depends on the complexity of your code and the type of service you're trying to provide. Generally, the type of naming, let's say I have some file CoreCpp, core.cpp file, which has my logic, then usually I would have some core API CPP layered above it that gives this type of functionality. And as I said, you can skip it often for small projects. Now, at this point, we arrive at one of the first very important boundary. Okay, of course, no business logic beyond this point. So, nothing we do from this point onwards or upwards can touch the business logic. Because if we'll see the diagram again, we'll see that some of our systems are already able to use whatever we provided. So any business logic we start adding in additional layers up here are already missing some of the systems that can interact directly with C++. If you think about iOS code, iOS can handle C++ code, so very often that's enough. The first two layers are sufficient to write an iOS app. But if we want to do Android as well, we still have a few more layers to go until we can interface with Android. So from this point on, there's no more business logic. Everything is just very thin layers of sometimes extremely disgusting code, but at least it's under our control, and I think that's the main importance here. So I called it, this is our third layer is the cross-platform public C interface, okay, the XCAPI. And I mentioned this before, the true lingua franca, the true language that is spoken everywhere of computing is C. There is no silicon today in the world, and I'm pretty much sure of this, that can run anything and can't run C. And one of the reasons is because it has a simple ABI, the abstract binary interface, application binary interface, which defines how you link programs, how functions are linked together. But many of you, most of you know the problems with C, and that's why we're going to keep it an extremely thin layer. And at this point, what we're going to do, I said we're going to use extern C for linking, so that we don't have mangling issues related that come from C++. We're going to do portable. This is the important thing here is the portable type conversion. So we're not going to touch platform-specific aspects of type. We'll see that in a bit. So we might convert, instead of an API, a C++ API that uses std string, we might start passing C++, car start. Because a C interface uses standalone functions, this is where it starts to be a bit ugly, the way we manage the object lifetimes. And that's why when we were thinking about object lifetimes at this layer, the cross-platform, the public C++ API, we had to keep in mind how the users are going to use it, because we have to think, are we going to use globals or singletons, or are we going to pass around opaque handles? We're also losing type safety at this point. So we're lowering our type safety standards, because what can you do? We're talking about C here. Of course, there's no function overloading. We have to rename. I'm going to show some examples. Again, the testing, mocking, and unit testing, but we're not testing functionality. We're mocking the interface. You see, I had your GSL talk, and this is exactly what our C wrapper says, is that when we go into our API itself is going to use C functions, because this is what we can export. But inside, we can immediately convert these things into higher level abstractions, like using GSL span or std string view. And naming conventions, I generally just insert the C function here, and I'm going to show some examples. So let's say I have this C interface. I define it extern C, and I'm going to say in a minute why it has the double quotes C. That's a good. It's not. No, that's intentional. A good catch. I'm going to talk about that in a minute. But you say we have two init functions. Again, these functions might have been actual methods called init, but because in C we don't have function overloading, so we need to give them two different names. Here we're passing our pointer and the size, like you said before about C APIs, and we have some ready function. Now, the reason it's called C with with air quotes is because it means it's not really C, it's C-like. Okay? The interface, it's a standalone function interface. It doesn't necessarily mean that it has to be pure C. And that's why I left the std string. I'm actually happy you caught that immediately, because it's an example that, this is a very practical talk. This is not about theory or any kind of academic purity. And in many cases, you don't really need to go all the way to C unless you actually do. So sometimes we can live with that, or alternatively, we'll see that in the cases where we do, we can do that in a higher level, in the layers up here. Okay, so we'll see that in a moment. I have one more example. Yes.
Experiencing relates just to name anyone's, right?
No, I know, but I'm joking that it's air quotes because for me it doesn't mean pure. It doesn't practically mean OSC functions. It means, of course, it's about name. For C++, it means name angling, right, to get the API.
As long as you're using the C++ compiler at this level.
Yeah.
Yeah.
Oh, yeah, I am actually assuming that you're using C++ compiler here because if we look at the implementation, this is the CPP file for the same.
You can go back.
What?
You're also losing the API stability because this string is might be different in each different implementation or lifecycle.
That's true, but that's only if you're actually exporting, and we haven't exported anything yet. Okay, so this is the CPP file corresponding to the H file we just saw. These 4 functions. The first thing to note is these are extremely thin. It doesn't get thinner than this. This is just a single return value. There is no logic. Remember, we passed the logic boundary, so everything is super simple. In this case, I'm just using I have full session. That's my core object. It's just a global in this case for the slide example. And the init function takes some string, calls init with the file name. This one calls init with the count on the global object, of course. You see the global. Yep. And process buffer. Here it uses GSL span, just what you see. It really was a perfect fit for me. Buffer plus size. And is ready is just calling the function is ready. Now, the nice thing about using, that's what you mentioned about using C++ compiler is that in my implementation of these C functions, I'm already lifting up the type safety by using these better abstractions.
This is implementation, but I mean, you want to take this header after you compile this and build it into library. You want to take the header to the next layer.
You'll see it in a moment. Exactly what I'm going to talk about. Another interesting thing, a note that I added, is that sometimes, of course, using globals isn't always the right thing to do, to put it mildly. And even the simplest example, sometimes you don't have an init function. You actually need to use a constructor. So in C++ 17, we have std optional to do that. So we don't need to allocate it on the heap with unique pointer. But even if you're using C++ 11, std unique PTR, a great solution. I've used it more than once in this type of situation. But of course, you can use opaque handles and other more common CAPI practices, which I won't get into here. Now, we just passed the halfway line, right? So we saw the first 3 layers. We saw our core with the functional and unit tests. We saw our C++ public interface, the XAPI layer, the cross-platform CAPI layer. And now we're going to cross the cross-platform boundary, okay? So there's no more this beautiful land of portable C++, assuming that exists for the particular subset of systems that you're using. And we're going to cross into this layer. Now, as I mentioned before, some of our target systems can already manage with this. So if you're using mscripten, well, mscripten could actually live here as well. So we could already target browsers and just write, well, mscripten really does need the CAPI. So things like mscripten, we already did enough work. So let's say I'm targeting simple desktop for a console application and some kind of web API with using WebAssembly or JavaScript, then maybe we can stop here. This is sufficient. Mscripten will take care of compiling our C++ code into WebAssembly or JavaScript. Our other compiler can target whatever platform we're using, and we're done. Swig is a kind of framework that generates bindings to other languages from C APIs. So it can also live here. But very often we do need to our functionality needs some interaction with the platform itself. And in this case, we need to go into our platform specific. We have to cross this boundary, the cross-platform boundary. And this layer, I call it, this is the platform boundary interface layer, right? So we're not talking about portable C++ anymore. We're not talking about portable C. We're talking about the place where you actually do go to Code Project or MSDN or to Apple's help or the Android, and we read about all these APIs of how to do different things. So this is where all the platform-specific code goes, where all the, if you're using Android, where you put Android.h at the top, this is where all your platform code goes. And we have to implement this, of course, for every target system. So this is where it starts to hurt. But we're not really duplicating any business logic. We're not duplicating functionality. We're only exposing our APIs to those aspects of the API that have to relate to the platform. We have to do things like conversions. I think somebody mentioned here about, I think you mentioned about things like, we'll see some examples later, but things like JavaScript in browsers, let's say image pixels are passed as RGBAs. There are always 4 values where we might use only RGB. So we have to do conversion. JavaScript only uses a floating point and not some other type. So this is the place where we do platform-specific conversions of data. We need to apply different constraints relating to how the data is used. There are different conventions. Well, I'll show some examples to make this more concrete. And this is a great place to put logging entry points. So if you want to log into the Android trace or to your syslog on your server, this is a great place to plug it into your platform agnostic logging framework. This is also the last place where we're reaching the module boundary. Okay, so on every platform, this is where we expose. This is the export layer of the DLL. Oops. This is where we have the boundaries, and we have to think about error handling. Most systems, if you throw an exception from a DLL, it will crash, or even worse, it might not crash. So you have to think about what you do in these cases.
It's not quite true. You can have the CRP itself as a DLL, the C++ standard library.
On Android?
Sorry?
On Android? In the browser?
This is only refers to that?
No, you have to implement this for every different target, and when you're crossing the boundary, you have to think about error management.
You're talking about the lowest common denominator.
No, I'm talking about thinking about error management. What you actually do. No, this is not. This is exactly the opposite, because then you implement this for every platform separately. So it's not the lowest.
This is never true. I'm saying this isn't always true.
Of course, nothing is always true for different platforms. Testing, let me know. I haven't found a proper way to test these things. I have an open Stack Overflow question that's been open for about 5 or 6 years. Nobody knows how to test this layer, for example, on Android. There is no simulator that can handle this. So here you have to do some mental backflips and keep your code as clean as possible. So let's see some examples. Again, we're going to use this exactly the same 4 functions that we've seen before. But in this example, we're looking at the, let's say, Windows or Linux DLL. Remember, this is platform-specific code. This is not, we're out of the cross-platform world. So we define our string C. We need this macro called DLL export, which translates to different things on Linux and different things on Windows, like imports and DLLs, all of these weird incantations. We need to decorate, we have to make unique names, and because this is unique in the global application namespace. This is not just our namespace, so we have to make all these really, really ugly function names. And you see that's the string you were very worried about. So in the case of Windows, instead of std string, I can pass these LPC str, which is a Windows string type, or MFC, or Win32. And the implementation, again, as simple as can be, as thin as possible. We don't want any functionality, we don't want any logic leaking into our layer, because this is horrible enough as it is, and we have to do it over and over for different platforms. So it looks a little bit dense. Most of it is completely boilerplate. let's look at the first example. Essentially, we're calling init from file name. This is, remember, the C layer. We're just calling the global C function with the string. The Win32 LPC str does automatic conversions to char star, which automatically converts to std string. Might not be the most efficient, but again, depends on your API. You can do it however you want. Sorry, what? Are you asking me Windows related? I'm a cross-platform guy. I don't.
No, yeah, cross-platform, but you're only considering the ASCII strings. It's also
in the slide, it works every time. It compiles on the slide.
Don't send smileys through this interface.
Yeah, real world question. This is all nice and it works well on a slide, but if the API is something bigger than just pass a file name or a couple of parameters to the function, you start, you might have actual API usage problems. For example, if you need to pass in a velocity.
Hold your thought. Ask me again when in a few more slides, okay? Because it's a good question. It's going to. I think I have the answer already. So, okay. Yes.
At this level, we can different DLL for each platform.
Yes. Exactly.
How to extend, how to
You don't, because it's platform specific.
So your distribution
This is Windows, for example. This is only for Windows. That's why it's so thin. It tries to. Everything else was abstracted away. The only thing, and for your question about ASCII, you're right. This is a great place to do the conversions. So if you know how to handle Unicode, and it's different between Windows and Linux, then the DLLs would handle it differently. Maybe on Windows you need to do some multi-byte conversions or stuff like that.
No, not at all what I meant. First of all, I didn't refer to conversions between ASCII and Unicode. And on Windows itself, you could have one binary build for Unicode and one for ASCII.
Okay, so that's kind of it works on the slide. The original answer stand.
It's very important what you've said before, because beneath it, if you would consider both ASCII and Unicode, in Windows at least, it's 2 bytes, right?
No, but you take care of conversion. Let's say you say I truncate to the right thing, but at least I'm not reading beyond the pointer. But
then if you do read behind the pointer inside your library,
but you don't.
No, you convert it here to a new container.
Yeah, you convert to a new representation.
It's not compiled.
You're not passing a pointer.
Here you already assume that your platform supports, for example, dynamic loading. And therefore, in the lower level, you didn't have to take care of naming decorated enough not to put it. But not every, this is not available on every platform. So how do you take into consideration in the lower level that you will be able to pack your functionality eventually as a DLL for the upper level?
No, but if your platform doesn't support binding to different language, then you're already not. It means that you already interface the lower level.
The functionality may be required on other system which does not need. The lower functionality should be usable for.
Yeah, that's why this goes all the way down. You see, the white part goes all the way down here because this layer can service everybody. That's why we kept all the business logic in here, because we know that some of our target systems won't go as deep as some others. I'm not sure. I think that's it.
I mean, your lowest level cannot assume that the name that it is using will not be exposed to upper levels.
So you have a Lincoln problem and you have to change some namespaces. Yeah, eventually.
He means if you know the
But it doesn't affect the other platforms.
If you know the normal name of the core, you can call that actually.
Yeah, but that's.
Right?
You can always hack your own system. That's what this is again, it's orthogonal completely. It has not really. Okay, so really, as I said, it's super simple. Do you see something strange here? Have any of you ever written this type of code.
It's usually for construction.
The function block
Why do you
exception.
it's not construction?
No, okay. Two things about the exception. First of all, of course, the ellipsis here is exactly what I want it to be. I want to catch everything. If there's something more to catch, I'll do it inside the body of the function. But in this case, I don't. But this is the module boundary, and we cannot afford catching and having anything thrown outside. Now I'm using this form of the try and catch are outside the block. I like this. I like the way it looks in this type of APIs. It's a kind of obscure C++ feature. But the fact that I'm actually catching everything regardless of what it is super important if this is a DLL. Let's say another example for Android. As I said, this goes on different platforms and it can look totally different. So in Android, you don't actually have an H file. The code is generated from the C++ file. And here we have to call this macro, the JNI export. We're already using JBoolean, which is it comes from the Android header, JNI header, which is the Javaized Boolean for the JNI interface. JNI is the Java native interface. And the JNI call, we have to append the Java underscore at the beginning of the names. And the rest, again, always, all JNI functions must call these two, always you have to pass the environment, the JVM environment, and some object and strings. And again, I'm still calling the same C functions, but here I might be doing some conversion. So let's say I have this JNI utils. It's a function that can get the file name in the Java string version. It generates some kind of C object or std string that I can call from, use my C function to call, and it will release the destructor will actually call the JVM function that releases the string. And the same happens for JNI bytes array adapter and so on. So this is a library I wrote a long time ago, kind of beyond the scope here. One nice thing is that I'm actually calling this exception handler function, which is another class that's included here. And this, for example, can catch an exception. It can rethrow an exception, check for its actual type, if it's, let's say, std exception, and then it can generate a JVM exception in the Java runtime and throw that exception inside the Java. So here, we're actually threading a C++ exception through the DLL interface into the JVM. So
basically throwing the exception in terms of Java?
I'm not sure, I'm actually translating. I'm creating a new exception in the language of the JVM, copying the string there, and maybe adding some additional information, finishing down here, but the exception is already percolating inside Java. As if it was a regular function, right? So,
why do you need the functions to be Boolean? Why do you need the functions to be Boolean?
Oh, just to say if it succeeded, for example. If in it, if not in it.
You don't always want to throw exception against a failure.
Because the failure is not always exceptional.
Yeah. It's orthogonal. It's, you might fail because of non-exceptional cases.
How does the exception handler?
It rethrows. If you call throw semicolon,
Yeah.
When you're inside a throw, a catch statement, you can call the keyword throw with a semicolon. That will throw exactly the same exception. It will rethrow the exception. So I can put it. Okay, that's really it's another talk. But I can have a try statement inside a catch, and that will throw the same exception again.
That's not exactly what I'm asking you. First of all, exception handler is that a constructor or a function?
Yeah, it doesn't matter.
All right,
whichever.
Okay, but doesn't it need a reference to the C++ exception?
No, because if you call throw with a semicolon, it throws the exception again. You can catch it.
And you can get it.
You can catch it.
STD least exception.
No, you don't even need that. You don't. There is a from C++ 11, but this goes back 20 years. You can just try catch and put the throw inside the try. Just throw semicolon.
Within the context of the implementation.
There's no whiteboard. Yes, we're inside the catch statement.
No,
No. In the context of the implementation of exception handler.
Yes. I'm calling exception handler inside the catch statement.
Yeah.
The implementation of exception handler has a try catch statement inside it, which is only called inside the external catch statement. And in that context, I can rethrow the exception and catch it with actual types, not with the catch-all phrase. Does it make sense? Yeah.
Maybe last question. Why did it return if it is false exception in Java?
Because there is a return.
Exception handler. Why did it return? If exception
Because
handler
this function is returning. This is C code or C++. C code.
I understand, but the return is in try. But if you have an exception and the catch value works, why did it return? Maybe because otherwise it will compile.
The C compiler doesn't know that it throws inside Java exception. So
Or pass,
But it doesn't throw. The thing is that this function doesn't actually throw anything. You remember, we don't throw from DLLs. We're generating a new exception inside the JVM that's going to be thrown in the context of the JVM. But this function actually finishes regularly. It might return 0 or no, false or whatever. Right? Okay. So the one before last layer, this is the native import layer. It's actually the very obvious thing you would expect. The only thing is that we're not in Kansas anymore. This is okay. We've left C++ land, right? This is the irony of, I call it uses the native interface, because the word native is actually overloaded with two opposite meanings. Because in Android, the so-called native language is Java. It's not C++. But then they call it the native interface call layer, and that means native to the processor, which is generally C. So I like to call it the ironically named native interface, right? So right now, remember I talked about skills of the programmers. I'm a C++ guy. I don't know JavaScript or Java or well, Objective-C is less of an issue here, but maybe this could be Python or Ruby or any other type or any other language that can bind or load C#, of course. So this is where we're actually going to expose these DLL functions. And I'll just skip to the examples. Again, we have integration testing, and we can call this, you see that the file names now have C# or JavaScript or some other type of whatever we're using on the target platform. And in this example, this is a very typical Java, but I think the C# looks almost find and replace a few keywords, and it's exactly the same. We define some kind of class. This is how you load the DLL from Java, and we basically expose these functions. If you go to the documentation on how you use JNI, this is what they tell you that the interface we defined in the previous layer. This is what it would look like. So remember we saw JBoolean, so JBoolean turns into the Java Boolean type. Or when we pass some kind of Java string, it's the string with the capital S. This is Java code. This is not C++ code.
Where does the marshalling of string happens between the two languages?
In my JNA utils get string function that takes as its first argument the JVM environment. So the JVM is the one managing this, and this uses kind of an RAI thing to call to say give me a handle to an array. I can copy that into my string or my string view. Then I call my init from file name, and when this line goes out of scope, the destructor is going to call the JVM and say, okay, now you can release that handle. Yeah, okay, so there is no implementation because all we're doing here is really exposing the DLL function names, right? This is like the dynamic linking part. And the last layer, I call it the interface wrappers, and I think this answers Greg's question. And this is kind of art, or I guess it's very platform specific, because here we're going to wrap these low-level interfaces that we just saw with abstractions that are more natural to the developer in that particular platform. So essentially, we're going to write now. This has almost nothing to do with the C++ code. This is we're changing our frame of mind and thinking like the target platform developer. So in this case, I took something more concrete. It's a slightly different example. But let's say I have some DLL called native face detector, and I load the DLL. It exposes some function called getFaceCenterPoint. And because this is really at its heart, it's a C function, the only thing it can pass through the interface is primitive C types, right? So it returns an array of floats. And in this case, it's an X and Y position of the center of the face. So, but I don't want to give the Java developer this type of interface because they don't think about points as an array of two floats. They want to think about it as an object from Android graphics point F, which is called point F, right? So in my same class, I can write a wrapper function, which is we're totally Java functions here, which is going to call the native function, which is going to run on the DLL. But in this case, I'm generating a point F. I can initialize it with the values from the array, and our Java developer knows nothing about the DLL.
Seems like the native function should be.
Sorry? Yeah.
Looks like the native function should be the previous layer.
It is the previous layer. This is the top layer. This is what the Java developer sees.
Static native. It should be one layer.
Yeah, this is static native.
They're both in the same.
Yeah, they're both in the same class. It should be private, maybe.
Yeah, maybe it should be private. Yeah, you're right. And I'll tell you a secret. This is how most Android low-level APIs are implemented. So everything people in Java writing Java on Android that are using the hardware or using the low-level operating system, this is the way it works. They just wrapped the C++ code inside Java classes, and the users of Java they don't know, they don't feel like they need to know about these things. So to summarize, we've taken a journey from the left to the right, where we start with our C++ core and we end with our application. And the application, of course, is somebody else writes it. This is the application developer because they're specialists. I'm giving them all the credit. They know how to write Android apps or iOS apps or Docker images or robot applications. They don't need to know if I'm an algorithm specialist or I know about business logic of accounting. They don't need to know what I know and I don't need to know what they know. But as an architect, I need to write a simple, practical way that enables all these people to interact together and to get all the benefits that I talked about. And through this journey inside these layers, as I hope it was clear, we're losing abstraction and we're losing expressiveness, we're losing type safety, because we're threading all the information through these lower and lower levels of interfaces and APIs. But these green layers allows us, of course, it's more work, but we can actually restore a lot of this functionality, a lot of these abstractions, so that the end user can actually feel safe and cozy within their own native environment. And I think it does give some kind of beautiful symmetry that we managed to regain all of this when we started with something so low level. Now, I don't know, what's the time? How much do we have? Oh, wow, okay. So this is a really quick example. Has anyone seen this parrot before? Are you familiar? On Slack, only people. It's a very common animated GIF of a parrot. And I wanted to show a practical example of this. Actually, I wrote a blog post that uses the Salami Method architecture to compile an OpenCV program to run in the browser. It sounds like OpenCV, I think Greg mentioned it before. It's a computer vision library. It's written in C++, highly optimized, and meant for doing image processing, computer vision. And it's generally, you don't think about doing these type of things inside the web browser. And I wanted to see how far I can take this abstraction, and on the way learn a little bit about scripting and JavaScript. So I'm not going to show all the code, I'm just going to give you a taste. But basically I have this function called rotate hue. It takes an image, a photo of a color photo with 3 channels. That's matte. In OpenCV, matte is the object that holds the images. 3B means 3 channels, each one is 1 byte, so it's an RGB image basically. And it returns another image. And what it did, it actually changes the hue of the image. So it kind of makes, just like you see the parrot here is changing color, in addition to moving, is cycling through the colors. So this is exactly what it does. And the H steps means how much it's going to do these cycles. So how far each call is going to cycle the colors. And clearall, it just releases some memory. So I mentioned before that for small applications, often you don't really need all the layers as separate code. You only need them conceptually. You need to understand the aspects. So in this case, this is our public, this is our core C++, but it's also our public API, and it's also our C API, right? Because this is just a C function. Again, this is the C with air quotes, because, no, sorry, this is the public C++ API. Now, because I'm not going to show, basically that code compiles into a simple console app and it runs on Windows. There's not much to do beyond that because the C++ app. But I wanted to run it in the browser. So now I have to go into that's the boundary interface layer. Now we need to fit this C interface into the type of services that JavaScript gives us, some scripting gives us inside the browser. So it's not just JavaScript, it's the whole browser ecosystem, the types and of the elements that a DOM tree gives us, for example. So we don't really need to go to look at the exact details here, but here, because we're in the boundary interface, this is where I'm allowed to include platform-specific headers, for example. So I'm including in scripting.h. I define these 2 global images. The reason I'm using globals is just to save, because I'm going to do it over and over and over, I don't want to reallocate images every time, so I'm just using them globals and hoping nobody's going to call this function multi-threadedly. But again, JavaScript doesn't know about threads too much, and I'm going to write the JavaScript as well, so all is well. And the interesting function, of course, is rotate colors. Now, the interesting thing to note is that this is a C interface. This is like a DLL interface, so we have to pass only very low-level data. So we need to pass the width and the height of the image that comes from the browser. But I mentioned this earlier, browsers only talk about images which have RGBA. So it's a red, green, blue, and alpha channel. So there are always 4 channels. But I wrote my function only to use a BGR, actually, not even RGB. BGR is the more common order. So because this is platform specific, my interface actually needs to get a handle, get a pointer to whatever the browser is holding, and I need to do my conversion. So in this case, I'm generating, this is the place where I'm lifting the pointers. This is kind of like the span equivalent. I'm lifting the pointers into an actual OpenCV 4-channel images, the input and outputs. And I'm doing some, I'm converting the RGB into the HSV. This is the color space where I can cycle my hue channel. The details are not that important. This is the core, okay? There's just one single line where all the action happens. And here I'm calling rotate hue. My colors are already, because here I'm converting, not converting HSV, I'm converting from RGBA to BGR. So here my images are going to be, I'm generating these 3-channel input image, rotating the hue with the proper number of steps, because I also got that here. And I'm mixing the channels. Again, this is just a clever way to switch around because they want RGBA and not BGR. Again, the details don't matter here. But then the interesting thing I want you to show is that I'm lifting my low-level data into high-level types. I'm calling my C++ code. and doing conversion. So that's really, it's the shim, really. It's where my real world meets my implementation. This is JavaScript code, okay? It's not pretty. Most of the code is related to how Emscripten can handle dynamic memory allocation. For it, generally you can't pass regular JavaScript arrays to Emscripten. That's not the limitation from my side. It's a limitation that comes from Emscripten, and most of this code basically does like a shared pointer memory management in JavaScript. It's not really important. The only place that's relevant, is the module is the name of the DL, the so-called DLL inside JavaScript. I call it rotate colors with the width, height, the byte. This is the equivalent of the pointers for the inputs and the outputs, and color change speed. That's some HTML variable that tells me how fast I want it to run. And at the end, we now reach this is the app level, which is of course HTML, because that's what browsers do. I generate some kind of just a placeholder called video plays. I can show I load my Java, my scripts. Color cycle asm.js. This is what Emscripten generated. Okay, so it's a JavaScript file, but you can't really read it. It's asm.js. It looks like assembly.
This is actually a layer that you didn't show. This is already the user.
Yeah, because here I'm the user.
Yeah, sure.
That's right. That's the host app. It's not even. You don't even have a user itself, because this is the app itself. But you're right. Yeah. And all I'm doing really is calling. I load the some kind of video for the HTML, and I add a slider, which this is the slider with the input tag, which gives me a slider to control the speed. So you don't think I'm not showing you a video. You'll actually see that I can change the slider. The speed of the color, the hue rotation is going to change. And this is can we see the HTML? I think I sent the files I sent you doubled. There's a URL link there. So I hope we can see it. But basically, you can go to my blog. This is the end of the blog post that describes this part of this application. And you see there's a slider here. Okay, maximize it. Just scroll up a bit. No, other than זה ממש too much. לך פרטי על זה. אז פה, show me. Okay. So on the left, this is an HTML video tag. This is what the browser does natively. Just put the video tag, and this is what you get. What we see here, this is our slider, which controls how fast the color cycling is working. And on this side, we're actually calling the function, generating the new frames, and showing them as separate frames on the right. Now it's going a bit slow because the computer is actually taping the video right now. So the computer is working really hard, but we can try changing the speed. You can see that the colors are changing much more quickly. So this is live C++ code running inside the browser. There is no backend here. This is not some kind of service. This is actual executable code doing image processing inside the browser on Windows. So, and I think this is really cool. And the Salami method really helps us manage writing such things, even though, as you saw, a lot of these layers are pretty disgusting to write, because you have to mess with different data types, different conversions, different standards, different conventions, strange APIs, but at least they're well bounded, kept inside and manageable. Yeah, and I think. Yeah, okay. So I wrote about both of these things in my, I have my blog, it's called videocortex.io. You can go and read about the Salami method there, and you can see the post about the pointing parrot. I think this will bring you there. And that's all I have for today. Thank you.